In this video, we're going to discuss aesthetics in GGPlot. First, let's talk about the visual aesthetics available for most GGPlot geomes. You may want to map an aesthetic feature to a variable or specify a specific setting. We must always begin by loading our library by either loading the Tidyverse library or the GGPlot2 library. Second of all, we're going to go ahead and load a preloaded dataset called iris by typing data iris. One of the most obvious aesthetic features you may want to change for your data is color. For some geomes, such as geome jitter, you can use the color aesthetic. However, for a few geomes, such as geome bar, if you try this, you may not get the expected result. You may think that changing the color in geome bar would change the fill color of the bars in your graph. However, this is not the case. Instead, what happens is that we change the outline color. So, how do we change the fill color for this geome? This is where we would use the aesthetic called fill. So how do you know when to use color versus fill? You can look at the reference or help information for each geome, but I typically try fill first, and if it doesn't give the desired effect, simply change the mapping to color. Knowing that these are both aesthetics to change color, let's look at the different ways we could use them. The simplest way to set a color is to simply specify the color of your choice. You can do that by writing either fill equals blue or color equals blue. GGPlot will recognize basic colors such as red, blue, green, and so on. If you would like to use a more specific color, you can search the internet for the hexadecimal color code of your color of choice. To add a hexadecimal color code in our aesthetic, we can use our previous example and simply replace the word blue with the hexadecimal code for a specific shade of blue. A note, in this code, my color mapping is outside of the aesthetics mapping. If you are simply telling R a color to make all of your data points, this is acceptable. However, we can map color to a variable. In that case, we'll have to specify the color inside the aesthetics. Let's set color mappings to a specific variable in an example. Let's look at the iris dataset that we loaded at the beginning of this video using the glimpse function and identify some variables we would like to plot. I'm interested in visualizing the relationship between sepal length and petal length, but I'm also interested in distinguishing which species each measurement belongs to. Let's make a plot visualizing how sepal length relates to petal length by species, like so. Adding the color variable to our graph has allowed us to see the distinct differences between species, and adding a layer of information to our plot while not overcomplicating the image. So in that example, we mapped color to a discrete variable. But what about a continuous variable? Let's look back at our dataset. In our dataset, we have some width measurements as well. Let's map our color to the sepal width and see if we can detect any trends. As you can see, GGPlot has provided a legend showing a gradient of color ranging from light to dark blue for measurements from 2 to 4.5. If we look at the data, we see an interesting and perhaps unexpected trend. First, for the upper cluster of data, which we saw in our previous example contained measurements from 2 species, we can see that these species do not have distinct sepal widths. Furthermore, there is only a slight trend, but the widest sepals belong to the plants with some of the shortest sepals. Next up, we can change the size of our data points. This is again fairly self-explanatory. Size is another variable that can be scaled to discrete or continuous variables. To set size, we specify a numerical value. Let's continue with our example of plotting sepal and petal length that we colored by sepal width. This time, let's change color to size. So here, we have the smallest measurements represented by the smallest points, and the largest measurements represented by large points. One problem that becomes clear here is the obstruction of small data points by large data points. We can use this final aesthetic we'll talk about today to fix this problem. As illustrated in our graph, dense and overlapping data points can prevent you from seeing certain data points or even determining how many data points there are. we can address this issue using an aesthetic called alpha. This aesthetic changes the transparency of your data. To set our alpha value, we will choose a number between 0 and 1, with 0 being completely transparent and 1 being completely solid. We will use 0.5 today. Now, when we look at our graph, we can get a much better idea of the distribution of our data points in the bottom left corner. In some areas, you see lighter gray points that don't overlap much, but for others, such as the data points in the bottom corner, we see very dense areas indicated by the solid black that tell us that there are a lot of data points in that region of our graph. Now you have the tools to enhance your plots using a variety of aesthetics. Happy plotting!